Okay, welcome everyone to week 7 of the superstructure component. And in week 7, we will learn 3 important topics. The first one is load passes. We have 2 types of load pass, gravitational loads or vertical loads, and we have also lateral loads. So this is the 2 load passes we need to understand this week to see how are the loads vertical or horizontal are transferred via the structure elements until reaching the soil or the ground. And next we will learn about the function of the bracing system in the steel structure, and we will draw the bracing layout, and we will also learn about the steel connections. Okay, and these are the files available for week 7 and up to now. This is the PDF or the lecture notes, and here is the tutorial question. And I have also uploaded a recording video to explain an example of the gravitational and lateral load pass. So you can watch also this recording. And after we finish this lecture, I will upload the lecture recording and add the link to this page as well. Okay, so now let's start with our lecture slides or lecture notes. So I will share my screen. Okay, so our first topic today is load pass, and the load passes are required in assessment or the superstructure assessment, part 1. So that's why I try to extend the due date for assessment 1 or for the part 1 of the project to give you some times to do this part. So our first topic today will be the load passes. Okay, we have 2 types of load pass again. We have gravitational load pass, and we have lateral load pass. Okay, so just before we proceed to the explanation of the load pass, just a quick reminder of what is the structures and what are the loads we have in our structure. So what is a structure? Structure is any form of construction used to support loads or resist the applied load or transfer the load to the ground or all of them together. So our building will be something like this concrete structure. So this building may be used as a residential building or office building or commercial building. And these slabs or these floors will have some loads, and these loads will be transferred through the columns and beam and so on until reach the soil. Another form of structure, this timber house. This small timber house may be used for birds or animals or something like this. This is also a sort of structure. And here we have some bridges. The bridge also is a sort of structure, or even this ship is also considered as structure. So any form of building or construction that is supporting loads or resisting loads or transferring load to the ground is considered as a structure. And the loads applied on the structure can be dead load or live load. These two are called gravitational load, or mainly are gravitational loads or vertical loads, because the dead load and live load are loads acting in the gravity direction or in the vertical direction, so they are gravitational loads. We have also wind load, earthquake loads, and snow loads. These three are forms of lateral loads, and they have also component of vertical load, but mainly they are lateral load. So our focus in this course is only up to the wind load, no earthquake loads and no snow loads. So mainly these three forms of loads are applicable on our structure or our buildings. Some other forms of loads like temperature loads or loads during the construction. So all of these are forms of loads, but we are not considering them in our structure. So the loads in our structure, in our course or in our shed are dead load G and live load Q and wind load W. So this is like a revision of what are type of loads or what is the form of loads we have to deal with in our course. Now let's have a look on how the load transfer in slabs or in floors and roofs to see how the load bus will be created or how we can explain the load bus. So for slabs or roof and floors, this is called a slab. So we have two type of slabs, one-way slab or two-way slab. So one-way slab means the load transfer in only one direction. That's why it's called one-way. In two-way slab, the load transfer in two directions. So if we have this form of one-way slab, so the slab is transferring its load to what? Beams. So in this type of slabs, we have a slab, and this slab is supported by some beams on the edges. Something like this. And also it can have some here as well. So the slab is supported by four beams, and these beams are on the edge like this. Okay. If the slab dimension, we have two dimension for any slab. So if we have one dimension, Lx and Ly, if we have Lx divided by Ly more than 2, or this means that Lx is more than double Ly, so the load will transfer in one way. So the load will transfer only in the short direction. So the loads all the time want to transfer in the short direction. So loads prefer short direction. So the load will prefer to transfer to in the short direction. This means that the load will transfer to this beam here and this beam here, and nothing will go to this beam or this beam. Okay, as you can see here, so the load is of the slab is transferred to the beam on the top, and the other half the beam on the bottom. So it is like you subdivide or divide the slab into two parts. The yellow part will go to beam 1, for example, and the pink will go to the other beam, which is beam 2. So this means that the load has transfer only in one direction, which is the short direction like this. That's why it's called one-way slab. Okay, so this for one-way slab. For two-way slab, if we have again slab supported by 4 beams, so the slab load will want to go to the beams. Here we have 4 beams and the dimension are close to each other. So for example, Lx over Ly equal to 1 or less than 2 in general. So if it is 1 or 1.1, so between 1 and 2. So let's call it, or let's write it as, if we have Lx over L1, Lx over Ly between 1 and 2. So if it is close, the dimension are close, so the load in this case will transfer in 2 directions, in this direction and in this direction. So part of the load will go to the top and bottom beams, part of the load will go to the left and right beams. So the 4 beams will carry part of the load. Okay, and this will be according to this shape here. So if Lx more than Ly, so it will, like, we make like 45 degree, 45 degree, and we have this part, 45 degree, 45 degree, this part. So this blue rectangle, triangle will go to this one, beam 1, and on the other side as well, we have this load will go to beam 2. Okay, and if it is like that, rectangular, so it will not be 4 triangle, it will be 2 triangle and 2 trapezoidal. So this red trapezoidal will go to beam 3. And the other trapezoidal at the bottom here will go to beam 4. So in this case, the 4 beams have contribute to carry the load or carry part of the slab loads. Okay, and as you can see, if we see here, part of the load moved in the vertical direction, part of the load moved in the horizontal direction. That's why it is called two-way slab. Okay, so in this slide, we learn how the load in the slab transfer based on the dimension of the slab or based on the 2 type of slab, one-way or two-way. In this example here, this 2 example here, this is an example of how the gravitational load path go through the element. So if we have a building like here, let's call it building 1 or building A. In building A, we have a slab. So this is our slab. This slab is supported by 4 beams. So we have 1 beam and beam 2 and beam 3 and beam 4. This beam is supported by columns, and each column is supported by a footing. And finally, all this footing are constructed on the soil. So how the load will transfer from the slab to reach the soil? Let's have a look here. We have done this before in a previous lecture, but let's have a reminder. So if you are living or moving on this slab, your load will move on the slab until reaching the beams. So if we consider this a rectangular, or sorry, a square slab, so this means that the load will transfer in two-way until reaching beam 1, beam 2, beam 3, and beam 4. So this is the first step. The slab will transfer the load to the beams. Okay, then the beams will transfer this load to, after the load reaches the beam will transfer this load through it until reaching this column and this column. This beam as well will transfer the load horizontally until reaching this column and this column, and so on. So the beams will send or transfer the load until reaching the columns. Then the load will move in the column vertically down, vertically down, vertically down until reaching what? The footing. So the column will send the load to the footings. So after the column, our load will go to the footing, the footing, the footing. The footing will send the load to the soil. So the final step after the footing is the soil. Okay. So the load transferred from slab or roof, or this slab means roof or floor based on the location of it. The slab send the load to the beams. The beam send the load to the column. The column send the load to the footing. Footing finally to the soil. Okay, do you understand this explanation for how the load transfer? Do you have any question about that? If you have any question, I can repeat again. Any question, guys? All good? Thank you, sir. Okay, let's continue to the second example as well to see what is the difference, if there is any difference. So the other example as well, similarly, if we have someone moving on this slab or this floor, so the slab will transfer the load in the short direction to the beams. So as you can see, we have beams in this direction. So the load will transfer in this direction first. Then, so from slab to beams. Here we have slab to secondary beam, because we have, as you can see, two types of beams. We have this beam, secondary beams, or something similar to purlins in our roof, for example. And we have also this beam and this beam here. These are main beams. So after slab send the load to the secondary beam, the secondary beams will send its load to the main beam in this direction, and so on. So the secondary beam will send its load to main beams. Then our main beams will send the load in this direction and in this direction to what? To the columns. So main beams send the load to the columns. Then the columns will transfer its load to the vertically down, vertically down, vertically down to what? To the footings. And finally, our footing will send its load to the soil. Okay, so the concept is similar. Whatever the shape of the building, the concept is the same. So you need to know how the load is transferred or what is carried by what. So beam is carried by column, column is carried by footing, slab is carried by beams, and so on. So this is the load path for gravitational or vertical load path. And now, if we look at this example from a residential building, for example, so if we want to make a quick explanation here, so if the load on the roof or the sheeting here, if you are here, somebody here, so the roof will be transferred to these beams. Then this beam will transfer its load to the top here and bottom here. Okay, and here as well. This beam is called ridge beam. Okay, so this is how the load is transferred. Then, as you can see here, this beam will transfer the load to this column, and this column will take the load down. Here, this ridge beam will transfer its load to this column here, and this column here, and this column here, and this column here, this column here. Then, for example, here, if we want to make a door or something, so we have added this beam. So the load of this column will be transferred through this beam here in this direction and this beam here in this direction, and then go back to the car. Okay, so this is an example of a residential building. Here as well, same. So we have the load on the slab or the sheeting to the beam. Then the beam will transfer the load to this beam here. This beam will transfer the load to these columns here. And this column will transfer to this beam. This beam will transfer to those beams here and those beams here in this direction until reaching this beam. This beam will transfer the load to the column down until reaching the footing or the slab or mat footing. Okay, so this will be transferred like that. Here as well, this beam will transfer the load to those studs here until reaching the footing down or the soil. Okay, so for any type of structure, you can apply the same concept to find or to show the load path. So the load path again need to be explained with sketches like this. So you need to show how the load is transferred from, for example, roof sheeting to purlins to rafter to columns to footing. Okay, so this was for the gravitational load path. Now let's have a look on the lateral load path. Lateral load path means how the wind loads are transferred in our buildings or our structures. So before we go through an example, So we need to know how we can resist the lateral load. What is the system or approaches they use or the engineers use to resist the lateral loads? So we have three options or three approaches or three possible approaches to resist the lateral load. One of them is the frame itself. So in some direction, if the wind coming in the frame direction, like this, so the rafter and columns can resist the load. Rafter and the two columns can be named as frame. Okay. So when we can use this approach when the wind load in the frame direction. So if the wind load comes in the frame direction, you can resist the wind load with the frame. In other cases, if the wind load is perpendicular to the column, perpendicular to the frame. So what this mean? So if we just add another page here. So if we have, this is our frame. So this frame, if the wind coming in this direction, so this frame is strong enough to resist the wind loads. But we have other cases for wind. What are those cases are? If the wind coming in perpendicular direction. So if this our frame, and in this case, the wind is coming in this direction. So the wind load are perpendicular to the frame now. So when you push this frame in this direction, this frame will fail because the frame is not strong enough in the perpendicular direction. So what we will do is, because we don't have only one frame, so we have several frames repeated each a distance. So we will make the frame strong by connecting each two frame with bracing. So when we connect these two frames together with bracing, so these purple lines are called bracing. So when we are pushing the frame in the perpendicular direction, the two frames with the bracing will work all together, so it will be strong enough to resist the wind in this direction. So if the wind coming in this direction, perpendicular, so this system, the two frames with the bracing will be able to resist the load or the wind load. So now we have two systems. We have the frame when the wind in the short direction or the frame direction. And system number two is bracing when the wind coming in the longitudinal direction of the hull or of the ship. Okay, so these are the main two we need in our project or our course. So here we have added the bracing to make the frame stronger in the perpendicular direction. Another system can be used, which is shear wall. And the shear wall are mainly used in concrete structures. Okay, and the shear wall is something similar to the bracing system, but it is in concrete structure. The bracing is actually or mainly used in steel or timber structure. But also sometimes they can use it in the concrete structure, but not common. So the main two in our course now are these two, or was this what we will be using? Frame and bracing. This is the main two. And for the bracing, we have two type of bracing, wall bracing and roof bracing. So as you can see, these are example of wall bracing. So the wall bracing will be strengthening the wall. That's why it's called wall bracing. And for roof, we have roof bracing, which will be support or resisting method for the roof, because each of the roof and wall are subjected to wind load. So we need to strengthen the wall and the roof with the bracing. And here is a comparison between wall bracing and shear wall. As you can see here, we have some bracing or wall bracing. So this is an example of wall bracing system. And on the right here, we have an example of shear wall. So as you can see, this is a shear wall and this is a concrete structure or concrete building. So as you can see, the wall is very wide compared to the normal column. As you can see, this is a column. So the column is very thin compared to the wall. So this is a column. And all of this is a wall or a shear wall. So the shear wall usually 5 times or 6 times the width of the column. So this is a shear wall, and the shear wall should start from the footing until reaching the roof. So it will be for the whole height. So this is a shear wall. Okay. So both systems are accepted to or are used to resist the wind loads, but the decision which one to use is based on the architectural nature of the building or the use of the building, sorry, the type of the material of the building. So mainly shear walls are again in concrete structures, and the wall bracing are mainly in steel or timber structures. Okay, do you have any question, guys? Do you have any question? Thanks, Yankees. So others, do you have any questions? Are you still there or you left? Thanks, Jörg. Okay, let's move to the next part. So now, if we have an example of a building or a shed, similar to the shed we have in our project or assessment, and to see how the load bus can be sketched or how the load bus is explained. So actually we have two direction of horizontal loads. So we have lateral load bus for loads in the short direction and lateral load bus for loads in the longitudinal or long direction. So in your project submission or in your project superstructure project, part one, you need to show two horizontal load buses. So if we look to here, the first one, short direction means when for a shed, we have this direction, which is our short direction, and we have this direction, which is our longitudinal direction. So the wind can come in two directions. The wind can come in this direction here, okay? When the wind come here, so the wind is in the short direction. So if we look here, we have bracing and we have frames. If the wind coming in the short direction, so the frame can resist these loads. So the green or the blue frame will resist the load because the loads in this case coming in the frame direction. So again, if the wind load in the short direction or the frame direction, this means that the frame will resist these loads. So the loads in this case will be transferred using this frame here, the blue frame or the green frame. Okay, so this for the short direction, the frame will resist the wind. For the other direction, the longitudinal direction here. So in this case, if this our short direction and this is our longitudinal direction. So if the wind comes in this direction, which is the longitudinal direction, parallel to the longitudinal direction. So if the wind load coming in this direction here, the frame will not be strong enough to resist this loads because the force in this case coming perpendicularly on the frame. So if the wind loads act perpendicularly on the frame, so we need bracing. The bracing will resist the load. So the bracing will resist the load. So as you can see here, when the wind coming in this direction, the frame is not carrying the load. What will carry the load? The bracing system. So this is the roof bracing. So this is the roof bracing, and this is the wall bracing. So the bracing will be the system which resists. So the bracing will resist the wind load. So similarly, in your project or in your shed, when the wind coming in the frame direction, it will be transferred by the frame. When the wind coming on the perpendicular direction, the wind will be resisted by the bracing. So again, these are the two cases. The first case, wind coming in the shorter direction. So coming in shorter direction means parallel to the shorter direction. So this wind parallel to the shorter direction. So the frame will resist. The other case, when the wind coming parallel to the longitudinal direction, so the bracing will resist. Okay. So in summary, for this type of building, we have two direction, X and Y. X is the short direction. So when the wind coming in X direction or the short direction, the frame will resist. So lateral loads in X direction are resisted by the frame in the short direction. When the wind coming on the perpendicular direction, or we can call it longitudinal direction. So what will resist? The bracing will resist. So lateral loads in the y direction are resisted by the roof and wall bracing in the longitudinal direction. So again, the red load will be transferred by this bracing. This is the roof bracing and this is the wall bracing. And when the wind coming in the shorter direction or the green direction, these frames, this frame or this frame, any frame will resist the load. Okay, so green by frame, red by bracing. Okay, do you understand the differences? So this is the load transfer or the load pass, gravitational and lateral load pass. And here is an example of a building. Okay, this example is already solved, so I put the solution directly for you. So if we can quickly go through it. So we have three load passes, as you know. We have gravitational load pass and two horizontal load pass. So if you look here, we have the gravitational load. So the gravitational load, we don't need to do all of these arrows. You just need to, for example, focus on part of it, of the building, like this one, for example. So what I have done is the load on the sheeting will go in the horizontal direction to what supports the roof sheeting. So the roof sheeting transfers the load to purlins. So those are roof sheeting, then the load will go to the purlins. So these are our purlins. right? Then the purlins transfer the load to what supports the purlin? The rafter. So the purlin will transfer its load to the rafters. So these are our rafters. So the load here and here go to the rafter. So these are the rafters. The rafter will transfer the load to the columns. So these are the rafters. So the rafters, those are rafters. So the rafters transfer their load to the columns. So here we have column. The column transfers the load down to the footing. So we have footing. So from columns transfer the load to footings. Then here is our footings. As you can see, this is our footing. So the load will transfer from the footing to the soil. Okay. So the load pass transfer from roof sheeting, then to purlins, to rafters, to columns, to footing, and finally to the soil. Okay. Do you understand this one? Just we'll change the color here. So this is our footing. So from footing to soil finally. So this was for the gravitational load pass. Then for the lateral load pass, we have two direction of the load pass, as you know. So we have in X direction or the short direction, and we have in the long direction. So if this our X, so the lateral load here acting in this direction. So who will resist? What will resist? Sorry, what will resist the wind load? The frame or the bracing? The frame. So here the frame will resist because the load in the short direction. So here what you need to do only, you will show that the frame will transfer the load through the rafter. So the load will go from the rafter then to the column because the rafter is supported by the column. So we have rafter, then column. Then the column will transfer the load to the footing. So as you can see here, we have, for example, a footing below this column. Then the footing will transfer this load to the soil. Okay, so this is how the load is transferred in the short direction. The third is the lateral load in the y direction or the longitudinal direction. In the longitudinal direction, as you can see, the wind is perpendicular to the column, to the frame. So if the wind is perpendicular to the frame will not be able to resist. What will resist? the bracing system or the bracing will resist the wind. Okay, so the bracing will resist the wind, not the frame itself. So as you can see, I will transfer the load through the bracing here. So for example, we have compression in this bracing because you are pushing here. So this will be under compression. Okay, then we have the cross bracing will be under tension. Okay, and this is for roof bracing. The wall bracing as well will resist the load. So you will have here and here. This will be also under tension, for example, and here as well. Okay. Then after that, the load will go to the footing. The footing will transfer the load to the ground. Okay, so this is the load pass for lateral load pass for the longitudinal direction, and here is lateral load pass for the short direction, and here is the gravitational load pass. So this example is you can follow to do the same for your project or your shed. Okay. Do you have any question about the load passes? So you mainly need to explain with sketch or show the arrows on the diagrams. You can show it in on 3D or you can show it on plan and side view. Yes, Jazir. The assignment has been extended to, I will check with you now. Can you all see the link of submission of part one? Just quickly because I have received a question. Can you all see this link? Submission link for superstructure? So the new due date now is 5th of May, Monday, 5th of May, 5th of May at 11:59. So midnight of Monday, 5th of May. Can you all see this link or not? Can you confirm, please? Okay, that's good. Is there anything not clear in assessment one? Sorry, the superstructure assessment part one. Anything not clear? Okay, so if we go back to our slides. So now we have finished the bracing, the load bus, and the next topic will be the bracing layout. We will have a rest for 9 or 8 minutes, and we meet back at 2:15. Is that okay? So we'll meet after 8 minutes to continue with the bracing layout. Thank you. Okay, so let's start our second topic for today, which is the bracing layout. So in this topic, we will learn how to suggest or propose bracing layout for our shed. So if we look to this example from the load bus explanation, this is a bracing arrangement for a structural steel warehouse. As you can see, in this building, they have added the roof bracing, and they have also added the wall bracing. Okay, the shape of this bracing was like only diagonal members. So we have one diagonal member in this case, one second diagonal member, third diagonal member, and so on. This for the roof bracing. For the wall bracing, they have also only diagonal member. So one option is for bracing is diagonal members. And we will see now another or more suggestion or more options for the bracing. This bracing can be in the first bay in one direction and on the like from one end and on the other end as well. So if we just remove this uh, roof sheeting, so we will have another frame here and another frame here. So if we remove this roof sheeting, we will have another set of the bracing on the other end as well. So we might have something like that. And for the wall bracing, we'll have also something like that. And here as well, we have. So this is roof bracing, and here is wall bracing. So this is a typical arrangement to see how the bracing arrangement, and let's now go to see some options of the arrangement for for wall bracing first. So for wall bracing, as you can see, if this our wall, so you can have diagonal members. This one option. Another option is cross bracing or X bracing. So here we have only like diagonals, members. Here we have crosses. So one option is diagonal, one option is cross. This based on how much is the force, how much is the wind force. If we have less wind force, we can use diagonal. If we have more wind, you can use cross bracing. Another option is the chevron. This this configuration is called chevron. So we have two diagonals starting from the middle. It can also be named as K. So like this is K as well. So it can called as chevron or K bracing. So we have two diagonal members starting from the middle. This is another option. First option is diagonal, but not in the same direction. So one in this direction, and then reverse it like that. So this also one option. Another option is knee bracing. So we have knee bracing starting from like one third, one third, and one third. So we have two diagonal, but in the starting from the one third. So all this bracing arrangement or layout for the whole bracing, you can assume in your project or in your report. So either of them will be accepted. But in reality, how they select based on the wind load, if it is low or high wind load, based on also the strength of the material of the bracing, based also on the architectural look of the building. So a lot of parameters need to be considered when selecting the bracing in reality. There's also different configuration for roof bracing in the plan view. In this slide, we will learn how, what is the frequency of adding the bracing. So if we look here, if this our plan of the shed, so here the bracing was added in the first bay each end. So we have the bracing in the first bay here and first bay here. So one option is two ends bay bracing. Another option in high intensity of wind, they can use double diagonal bracing over two bays from each end. So instead of one bay, so they have used like two bays. So each one of them is a bay. So one bay, bay. So here is only one bay. So one option is to arrange the bracing in the first two bay at each end. Another option is instead of add the bracing to the first bay from each end, we add it to the second bay from each end. So this is another option. Another option is only add the bracing in one bay randomly in the middle, and this bay will resist all the wind. And another option is adding the bracing at each end, the bay of each end, but instead of diagonal, we can add it, sorry, instead of cross, we add diagonals. So this one option as well. So in our case, we can focus on the first option. So we can add the bracing, like cross bracing at each end, for example, or whatever you want from here. So all of this are accepted. So again, it based on several parameters like the availability of the material and the intensity or the how much is the wind load applied and so on. But in our course, we only focusing on drawing or sketching the wind or the bracing layout. So we are not designing the bracing, we are just drawing the bracing layout. So the plan given to you in the project as empty plan, and you need to suggest a form of or arrangement for the bracing. Okay. And here is one example similar to the shed, but different so that you can try yourself in the project. So we need to sketch the bracing arrangement for the given warehouse. We have three view. So we have, this is the plan view. This is the side elevation. And this is the front elevation. So in this case, we need to draw the arrangement of the bracing. So we have wall bracing and roof bracing. I will start with the roof bracing. So one option, if we do the same like the first one here, so we will add the bracing at the first bay, something like this. And the last bay. So this is our roof bracing. Okay. For the wall bracing, we will add to the side elevation only. So we will add, sorry, for the wall bracing, the wall bracing is needed only on the side walls. No need in the front wall. So we will add bracing in the same base of the roof bracing. So wall bracing in same base of roof bracing. So if we add the bracing here in first base, so we will add the wall bracing in the first bay and also in the last bay. Okay, so this is the side wall bracing or wall bracing. No side bracing needed here because the frame is strong enough to carry the loads. Now we just need to add some small thing. We need to show the side wall bracing in the other drawing, and we need to also show the roof bracing in the other drawing. So how can we do it? The side wall bracing will be shown as a small cross here and a small cross here to show that we have added side wall bracing here. So this is indication of side wall bracing. And similarly, we will add a small X here on top, small X here on top, This small X show the roof bracing. In this drawing, we will also show the side wall bracing here and the side on the side, just to show or indicate that we have side wall bracing, and on the top, a small X here, a small X here to show the roof bracing. So in this example, we have shown the wall bracing and side wall sorry, the roof bracing and side wall bracing in both plan view and front elevation view and side elevation view. Okay, so this one option. Another option is here. So if you select to arrange the bracing only on one bay in the middle. So I have add the bracing here in the middle. So this is our roof bracing. This is our side wall bracing. These lines are side wall bracing in plan, roof bracing in side view, and these are wall bracing and roof bracing in the front elevation view. Okay, is the bracing layout easy? Do you have any question about the bracing layout? So again, the bracing layout is just a sketch of the bracing without designing the bracing. So we are not designing any bracing. We're just suggesting or proposing the bracing layout. Any question, guys, about that? Do you have any question? Nothing? Okay, no worries. So let's proceed. So our third topic will be about the steel connections. So in steel, we need to connect the member together, like connecting a beam to beam or beam to column or column to column. So we have two type of steel connection, as you can see. The first type here and second type here, we have bolted connection and we have welded connection. So two types of steel connections we may have in our structures, bolted using bolts and welded using weld. So here there is a video showing the steel frame construction. So let's have a look on this video. So guys, have you heard any voice? I couldn't hear any voice. I don't know why. Seems like the video doesn't have sound. Anyway, have you understand the video? Do you any question about the video? It show how the team members are connected together on site to create the frames and so on. Any question about that? Okay, so let's continue. So let's start with the bolted connection. For the bolted connections, we have type of connection called column to beam connection, and first type of column to beam connection is simple column to beam connection. So for simple column to beam connection, we called it as simple connection, or we can call it as shear connection as well. In these connections, we are connecting a beam to a column. That's why it's called column to beam connection. But this connection is simple or bin because only the web. So as you know, any section, I section or H section. So any section like that has web and flange. So this is the flange and this is the web. So in simple connection or bin connection, we are only connected the web of the beam to the column. So in simple connection, this one important information you need to know. For simple connection, only web are connected. So that this connection only transfer shear. That's why it's called shear connection. Okay, so as you can see here, we are connecting only the web to the column. Here, as you can see, the flange of the beam are not connected to the column and only the web is connected. This one example from real life. So if this our beam here and this is our column and this is another beam. So as you can see, the connection here is only the web. So only the web is connected to the column. Only the web is connected to the column. No connection at top, no connection at bottom, no connection here, no connection here. So this is called again shear connection because we are only connecting the web. This means that this connection can only transfer shear and doesn't transfer moment. That's why it's called simple connection. Other type of connection is the rigid connection, rigid column to beam connection, or fixed connection. In the fixed connection, we are connecting the flanges. And sometimes we can also connect the web. So if we are connecting for rigid or fixed connection, we need to connect the beam flange to the column. This is the main difference. So connect the flange to the column. As you can see here, we're connecting the flange to the column. We are connecting the flange to the column. And also we can connect the web as well. Okay, this is something similar to this connection here. As you can see, the flange, the web, and the top flange are all connected to the column. This is also another type of the rigid connection. So there is this rigid connection between the rafter and the column. So we are connecting the web and flange. So here in this connection, both web and flanges are connected. So we have two type of connection, simple and rigid or fixed. In the rigid connection, what is the advantage or what is the probability? The rigid connection transfer moment and shear between beam and column. For the simple connection, we are only transferring shear, doesn't transfer moment. So this is the main difference. So in our project or in beams or this, you can see this in your project, but what is the difference between bin or fixed connection, or what is why we select a bin or fixed connection? So for example, if the beam starting with hinge or bin connection and end with bin connection, so this is called bin beam. So if this our column here and our column here, the connection between the column and beam are is bin connection or simple beam to column or column to beam connection. If we have a column simple column to beam connection, this means the moment at the start and the moment at the end is equal to 0 because no moment at the bin. So when you have a load, a uniform load like this will be our moment. So as you can see, the moment here will be high moment. The value of the moment in this case will be high on one side. But if we have another case, we have a connection between the column and the beam is rigid or fixed connection. So if we have this is our column and this is our column, the connection between the column and beam is a rigid connection. So we have a rigid column to beam connection, or we can call this beam a fixed beam. So here the moment is not 0 at this point and this point because the moment between the beam and column will transfer so that M here has a value, M here has a value. So the bending moment diagram for this case will be something like that. So here we have the same value, but this value is distributed between two sides. So we have negative moment here and positive moment here. So here on this section, we will have less bending moment or less moment. Here we have high moment because all the moment on one side of the beam. Here the moment is distributed between two sides. So some cases we need the fixed moment, the fixed beam to reduce the moment on the beam. Okay, so this one advantage or why we are using the bin or fixed joint or fixed connection. And here is another example for our frame. So what would happen if the builder accidentally changes the connection type. So for example, if you want to make it rigid and unintentionally or accidentally, the builders change the connection. So if this connection is a simple connection between the column and the rafter, so if this our rafter and this our column, so here we have bin connection. So all the moment, as you can see, will be like that. So this is our moment. We will have a high value of moment, high moment here. And actually, the designer or the engineer designer has assumed this is a rigid joint. So if this a rigid joint, so the moment on this beam should be something like that. So we have negative moment, positive moment, and negative moment. So here, all the moment has been distributed between positive and negative. So here we have less moment on the beam and we have less moment on the beam. So if the builder changes the connection, this may cause failure or collapse of the building because the designer didn't include or didn't assume that all the moment will be positive. So his design was half positive or part of the moment positive, half or part of the moment negative. So now the moment will be higher than design, and this may cause the collapse or failure of the building. So that we need to make sure that the construction following the design, otherwise failure could happen. So this is the difference between the rigid and simple connection between beam and column. And here is another connection we have, which is the support. For the support, we may have hinge or pin support, something like here. This is a bridge support. The hinge support is something like this. This is how it is structurally shown or presented. So this is hinge. The main criteria of a hinge is it allow for rotation. So the hinge is allowing for rotation. This is the main property of a hinge. As you can see here, here is a hinge as well. So this hinge is allow for rotation. Here as well, as you can see this hinge in a normal building, allowing for rotation. So if you want to allow for rotation of your column or your beam, you need to provide a hinge support. So the hinge support has this symbol. Another support is fixed or rigid support. The fixed support is has the symbol like this. So this is the fixed support. The fixed support doesn't allow for rotation. No rotation allowed. So if you want rotation, go to bin. If you want to prevent rotation, so go to fix it. So in this here, in this support here, if this our column, So our column is fixed to the footing. Fixed to the footing by those bolts. Okay, and also we need to have embedded length of the bolts inside the footing to prevent the rotation. So as you can see, the bolts are embedded for a distance, whatever the distance is. So this length is the embedded length of the bolt. So if when you have more moment, you need more embedded length to avoid rotation or to prevent the rotation of the building. Sorry, of the column or of the support. Here is beam to beam connection, similar to column to beam connection. We have two type of connection, shear connection and moment connection. So you can have a look or you can watch this video. Yes, yes, just there is holding down bolts. Otherwise, if the moment is high moment on the footing, this bolts, if they are not embedded enough, they will like get out of the footing and the column will fail. So there is a relation between how much is the embedded length and how much is the moment. So, but we are not designing that, so we don't need to worry too much about it. But more embedded length will give us more moment or more fixation to the column. Okay, so similar to beam to column connection, we have beam to beam connection. So if you connect the web, it will be a shear connection. If you connect the web and the flange, it will be a moment or rigid connection. You can watch this video to see the like several types of beam to beam connection. And here is the difference between welded connection and bolted connection. You can watch it quickly.
This rigid or moment connection connects the web of the beam to the column through bolts and the flanges of the beam to the column by welding. With this connection, the beam cannot rotate unless the attached column also rotates.
Okay, so this was a quick video. In this video, it is a mix, a connection between welded and bolted connection. So in some cases, you can use bolted and welded connection at the same time. So in this case, this is a column and a beam. So it is a beam column connection. They connect the beam flange to the column by weld and connect the web of the column to the beam by bolts. So we have bolted and welded connection at once. So what is the difference between welded and bolted connection? We know already the bolted connection. For the welded connection, you are connecting two parts of steel by weld. We have two type of weld. One type is called butt weld. Another type of weld called fillet weld. So in butt weld, you need to make a cut between the two parts. and then you fill this part with the butt weld. So this is butt welds. For fillet weld, you have already this part and this part, and then you just no need to cut, so you are fillet this part together with a fillet or fillet weld. So these are the common two types of welding. And the welding is using, I don't know if you have, it is a gun with a material in this gun, like holding this gun, and this is the wire, and this is the gun, and then they are applying heat on this one. So this heat will make this metal melt, and this metal will fill or will make the weld for us. Okay, so this one type of connecting steel parts together instead of bolt, you can use weld, and you can search. One of the question is what is the advantage of welding and what is the advantage of bolting connection. So one clear advantage of the welded connection is you don't need to make holes to connect the member, because in bolted connection you need to make holes so that the bolts will go through the members or the elements. So you can search about the advantage and disadvantage of each type of connection. And here is some of the shapes of butt welds. So when you are connecting two pieces together, you can make square, so you didn't cut anything from each part, or you can make a single bevel, so one part is straight, one part with bevel, or double bevel, or single V, or double V, or W, or single U, or double J, or single J. So all these are forms of connecting two pieces of steel together with the butt weld. So we are not going into details in the welding or welded connection or bolted connection. We only have one like question about it, no calculation, but just to give you some background on the connections. So this is for the butt welds, and we have some problems in the butt welds, as you can see here in this real photo. So some of these problem or defects are undercut or cracks in the weld itself, or porosity, or slag inclusion, or lack of fusion, or lack of penetration. So all these are problems associated with the butt welds. So porosity, for example, means there is some air voids inside the weld, so this will make the weld weak. Undercuts mean we have some, like, we didn't fill all this part here because of some settlement or some leakage of the weld at the bottom. Cracks means that we may have cracks in the weld itself. Slag inclusion means there is some impurities inside the weld, which make it also weak points, and so on. So you can also have a look on these defects and butt welds. And here is fillet welds, some of the shapes or forms of fillet welds. So for example, here we have fillet weld 8 mm leg on one side. So we have one side here. Here we have fillet weld for both sides, but one side is 8, one side is 6, one side is 12. Here both sides are 8 legs. So for the fillet weld, you may have one connection only or two connections based on the force transferred between the two, and so on. So these are some shapes and some information about the fillet weld as well. So you may search about the differences between butt weld and fillet weld, and which one is more like more advantageous, or what is the advantage of each of them. But we don't go through them in detail, so just have a look on it. And these are some defects of the fillet welds. So this is an example of good weld. This is a bad weld because as you can see, here is some erosion in this plate, and some also residual parts of the weld here, and the weld is not covering both plates with same leg. So if it is designed to have same leg, it should be something like this. So here we have another bad weld, narrow and excessively convex. So you have convex, it need to be concave, and also irregular contour. Here is excessively wide and flat with is better. So here it is wider than here, and irregular contour, poor penetration along edges. So this also another bad weld form. So all of this, you can also have a look on it, the defects in fillet weld. So now in the connections, the main thing you need to know in summary for connection, the difference between simple and rigid beam or column to beam connection, and the hinged support and fixed support, and again the simple and rigid beam to beam connection, which is similar to the column to beam connection, and the difference between welded connection and bolted connection, and the two common welding connection or welded types, which is butt weld or fillet weld. So this is mainly what you can read about in connections, and we are not designing connection in this course. So we have only one question in the assessment, so you can have a look and make your own research about it. Okay, and thank you for attending the lecture today. Do you have any question, guys? Any question today?